Okay. Hello everyone. Good morning. So I hope you guys already scanned the QR code. Uh, yeah. Yeah. Morning, Police. Yeah. Okay, by the way, do you have any other course besides the calculus, and you have the introduction to engineering, right? Besides those two, do you have any other course? The Friday chemistry afternoon. Oh, okay. Okay, chemistry. All right. I think we can start. Okay. So yeah. So maybe we start from the feedback from the last Monday. Um, this is to review the product rule and the exponential function. And actually, I put some, yeah, I think one additional video about the uh, exponential, or precisely about the E. It's actually what we have done in class, but I'm explaining a little bit more. So if you want, you can go to check the video. Uh, I'm I've been attached. I've attached the link to the video on the Google Classroom, and I think I will also attach another link later regarding to the quiz. So I've checked. I think all of you already graded, but not yet returned the score, because I need to check. I think there are one or two students who are not using their real name. So yeah, I still figure out who was the student. I will put later in the Moodle. Uh, okay, so first let's see the product rule here. I think the exponential is one of the I think one of the most important functions in a calculus, because when you derive the E, it will get this E. So we can use this exponential in terms of uh, most of physical phenomenon that has related to rate of change. So this is every rate of change can be uh, can be described by at least by E. Okay, like for example, the temperature, the Newton, how the name is, the cooling temperature, the populations, and also in finance, everything that has rate of change, we can describe all with E. Okay? And here, the question is asking if you have this function here and everything all written here, the g with 0, g prime 0. So you need to just derive the functions, and you get the product rule, right? You get the product rule, you put in 0, you see the information here, and you get the answer is 7. Okay. And I think my suggestions for you, if you are still get in touch with the derivative, you can go slowly. You can go slowly, and you still can solve this problem. Okay, you still can solve this problem. Okay. All right. Now the next question, and I think this is a typical question in calculus. Every time you see in every chapter in calculus, you will see most likely this question will arise. Eventually, when it's come to derivative, you will get the questions, find the equations of the tangent line. Okay. This question, find the equation of tangent line to the curve that parallel. Okay. So parallel means they have the same slope, so same slope. And then if you see the curve itself, we can check the first derivative to get the slope, okay, at that point. Okay. And what we are going to find is we are finding the x, or if you want to make it clear, you can also put some other variable here to indicate that this is the point that we are looking for, point A, if you want. So you are not mistaken with the variable x. And then you get that when you plug in x to when the a plus 1 is 2, you get x is 1, and then y is 0. When you get x negative 3, y is 2. So you have two possibilities. Check both line and check the options. Then I think the only one that has a correct answer is this. So this is the quotient rule. And I think when you get more and more familiarized with the derivative, the name, the rules, it doesn't matter if you forget. It doesn't matter as long as you remember the technical solution. That's the thing you need to remember. And if you feel like you forget something in calculus, you can always derive the whole formula from the principles. I will show you how. If you forget, aside from using limit definition. Of course, you can use limit definitions, find some prove some concept, but probably if you feel the limit definitions takes too much time, there's another way to derive the whole formula, especially in derivatives. Okay. Later, I think I can show you. I think today I can show you how. Okay. Okay, so congratulations, Jimmy. Okay. Okay, now let's get to the feedback. Give us more time in the quiz. Okay, yeah, sorry for the short time. For the quiz, it's, each question having timer is actually a good challenge, I thought, for you. But probably the next quiz, if we have the quiz in online platform, maybe I will add more time to the timer, because I'm setting the timer so that you can focus on the questions. And I think that is needed for some restrictions. Okay. And then, we know the question that we got wrong. Yeah, I'm working on the video about the quiz. So hopefully this week I can upload the video, then you can review. Because if I review the whole thing in the class, I think we don't have that much time. Okay, so difficult, become more difficult. Yes, it will become more difficult. Eventually, the next calculus, the next semester calculus is much more difficult. Explain the e function part, and then this is why the slope in x0 is 1. Is it the definition? Oh, that's it, because e with the power of x here. The slope is 1 because in this point, when you have e to the x and you differentiate, it's just e to the x. And if you are see this 0 here, then you put in 0, then it's become 1. Okay, that's the e. And then what is e? Check my additional video about e. So actually, if you are looking here, if you are observing this 2 with power of x and 3 with power of x, then at the middle, you found the number e, in which you can actually rewrite the whole thing. For example, if this is having, if you want to derive this, this become still there, but it has other constant. And if you are deriving this also, this is having another constant that is proportional in the graph. And you know that because this happens, this ln happens because of e. If there is no ln here, then this is maybe just a constant number, something like that, or maybe here something like that, just another number. And we know the number when we learn e. Oh, that is actually ln of 2, then it will become 0.69, and etc. So here you can also rewrite this and becomes, because you can always rewrite this in terms of, so everything in exponential, you can rewrite all of them in terms of e. And that is, I think, one of the most important functions in calculus. Okay, that's a little bit about e. You can check the additional video. Okay, next thing is we are going to learn a chain rule. Okay, chain rule. So this is, I give you this definition first, and let's for maybe around 10 to 15 minutes, let's try to prove the chain rule, okay, using some epsilon. So first, the chain rule are named chain rule because it seems that you have a long chain. So you have a long line of chain of derivatives. Okay? So if you're looking here, this is the first derivative, right? And you can rewrite this first derivative and connect them to other variables as you want. So for example, you can write as long as possible as you can. Or even like that. Or you can also make it longer, longer, and longer. And this long line is based on how the function is composed, the combination of the functions. We learn about the composite functions, right? The composite function, the f, and then the g of x inside f. And it doesn't need to be two functions. It can be 3, 4, 5, 6, any number possible. Like for example, you have g, and then you have h, you have maybe k. It can be more and more, as long as it is composite and all the functions are continuous. So we can, and we know that all functions differentiable. Okay, so that's why it needs to be written that all differentiable at x, these two functions, both differentiable functions, and we can use this chain rule. Okay, now if you want to prove the chain rule, we start with some definitions. First, let's say let y is equal function of x, and x changes from some a to a plus a delta x. So it has an additional delta. So first we define y, and if we have a delta y, then this means the height difference in graph. So if you remember, if you have this, then you have this triangle. This is the delta e, the delta y, this is delta x. Okay, and we use limit to approach the delta x to 0, and write the delta y divided by the delta x. This is, if you remember, we are in the early definition with limit and rate of change, and this will be limit. We can write also delta y divided by delta x, and we can also define this as our derivative as we have done before. And then we use epsilon, or maybe not, let the epsilon be a difference between delta y and delta x and f prime of a. So this will be, how to say, because we are defining the derivative with limit, then in actual reality, because limit is to indicate that there are really, really small gaps or small numbers that are close together, that makes some points close together, then in terms of derivative, we are ignoring that small numbers, right? Actually, we are ignoring that. But let's say we have an epsilon, the actual number in between the delta y over delta x and the f prime of a. Okay, so we have this definition: limit as delta x approach 0. We can also write this in terms of this. Okay, based with what we have learned, we know that this is actually the f prime a, and it should be 0, right? It should be 0. It should be 0 or close to 0 in limit, right? But we need to say that the epsilon is still has some small value. So we need to keep this epsilon for proving our chain rule. Okay, we need to keep this epsilon. Okay. Okay, now first, let me look at, okay. So first, let me having the delta y is f prime a delta x plus epsilon delta x. So as epsilon getting 0, so epsilon getting 0 as delta x getting 0. And if the epsilon defines as 0 when delta x is 0, then we can say that the continuous functions. Okay, let me write more. Suppose we have u defined as a function of g of x, and then y, another y. Y is a function of u, yeah. And then this is differentiable at a, this differentiable at b. But b is g of a. I think we can copy this first. I need to go into the next page. I hope you finished to look at this note. But let me finish the writing first, and then I can move forward and backward if you want to look the notes, okay? Let me finish first. Okay. And then if the delta x, delta y, delta u, this is all indicates the small increment. Increment means a small size, really small. Small increment of x, y, and u. And then we can also write down the delta u is the same thing as the first one. So delta u will be, we are going to use the g, okay, g prime a. We are going to use the number a here, delta x plus, let's say we have another epsilon 1, okay, to take the difference between the first epsilon we have in y, and this is the second epsilon, delta x, okay? And then we can, let me write, and then we can also as the delta x getting 0, then the epsilon 1 also getting 0. Okay, so the first equation is the general, let me write, so to make it clear, this is general equation. Okay. This is another case, okay, you have another case that u and y we are going to put into the chain rule formula, okay. And then we have the third one is delta y based on f of u here, and differentiable at b, let's use b, f prime b, delta u, okay, plus epsilon 2 delta u, because we are now evaluating with respect to u, right? And the same thing here, we are going to have f prime b plus epsilon 2, and as delta u closer to 0, epsilon 2 will be also closer to 0. Now let's combine equation 2 and 3. So delta y will be, so we are going to use the whole delta u here and going to put here, okay? And combine. plus epsilon 2. Oh, maybe this is, we are going to put here. Okay. Delta U is G prime of A plus epsilon 1 dx, or delta x. So our delta y, delta x is f prime b plus epsilon 2 multiplied with g prime a plus epsilon 1. Now, if we define dy dx as limit as delta x approaching 0 of delta y over delta x, then this will be our definition. And then as delta x closer to 0, the epsilon 1 and epsilon 2 also closer to 0. And this will be our definition. Or we can also write b in terms of g as we have defined before, that this is true for the chain rule. Okay. I think this definition or proving this chain rule, the important thing is not to memorize all of these things, but the important thing is to realize that if you want to prove any derivative using limit, then we are going to use some epsilon so that we can know that there are still some actual value that is still there. Okay? Because if you are looking at the limit, uh, it's actually our approach, right? The limit is our approach, not the real value. If you are thinking like when you touch the wall, you are not really touching the wall. You're maybe just like slightly feel the surface, not really touching the surface. That's how limit works. And because it's really close, in derivative we kind of ignore it. It seems that we are ignoring. So in terms of proving most of the derivative, uh, I think it's best to work on with limit. And in this case, because we are looking for uh, the concept of derivative, we need to bring on some epsilon, that is the difference between the derivative itself with the limit, with the limit of the y, delta y over delta x. Now, in more practical approach, let's see here. In more practical approach, if we have, um, let's say we have y sine x and then square. Let's say from the simple function, and we want to look for the first derivative, the y prime, right? So the idea on how chain rule works is, if it is simple enough, I think you can go directly. You see this, the whole here. You can say that this is the outside function or outer functions, and you can look at the middle here, the inside function. The outside functions, it has something squared. You can name this as x squared if you want. Maybe if you want to work slowly, you can work naming all the function first, and then g is sine x. Then this is is fog. Then this will be sine x and then squared. We can work like that, naming all the function first, and then uh, looking for each derivatives and then combine all together at the end. That also works. Okay. But if you're already familiarized, you can directly straightforward you looking at this function. Oh, it's not too complex. Then we can work directly derive to the something squared. So you have two something here same, and this is the first one, and then multiply with the inside functions of sine. This will be cos x. Or if you prefer, work on the work on this. You have f prime, or maybe if you work write f g of x, f prime here, then this will be, and then we can start by looking at this. Start by f prime is x squared, f is x squared, so it's 2x, but inside it's gx is sine x, so 2 sine x, and then this g prime is from sine becomes cosine x. We can also work like this. Okay. Depending on how you approach the chain rule, uh, it doesn't matter. It doesn't matter as long as you are keep consistent, and finally you will get the final results. Okay. So I think that there's also a strategy if you are thinking about calculus. A strategy. So calculus itself is more about how you find the derivative, how you find the integrations, right? So in this case, strategy, you can start with calculus or you can start with algebra. Maybe later, if we have more complex one, you will see which method you prefer. Sometimes you see some function that, oh, I think I can derive this directly. But then when you derive, it become more complex, and it seems that you need to write a lot of numbers. So maybe you can simplify the function first and then you can derive after that. That's also possible. So you can do directly calculus, derive something, or you can maybe simplify the function first and later you can maybe get more simple results. But I believe both method has the same result, Like for example, maybe start with this. I find the first derivative. Okay, I think this is not difficult. You can start with the outside function, and that is just 1 over 2 x plus square root of x, and then let me write maybe all steps here. Inside function is this. Then I can write this as 2 square root of x plus square root of x is 1 plus 1 over. And yeah, you can stop here if you want, or if you want to simplify, you can simplify. It depends on the requirements of the questions. And try to think this one. Can you solve this one? So it's square root of x plus square root of x plus square root of x plus square root of x, and it's going to be forever. So this is quite a tricky problem. But to solve this, I need other tools that I will show you later on after this section. Okay? So let me mark this, and let's go back later. Maybe in near the end of the class, let's go back here. Maybe I'm giving you another example problem. See if you can get it correct. So if you have, so let f the question is f prime 1. Yeah, this is just for practice. See if you can get the idea behind this function. The I think quite complicated composite. And for online students, you can also try. You can write down the number in the chat box if you already found. This is to practice. As long as you work maybe slow and focus, I think you will get the result. They give you some quite few times, few minutes. Okay, so the idea behind this composite function is there is another variable here, another variable here, right? It's another variable xf that probably you should do some product rule when you need to derive the inside function, right? So you derive f prime something, and then you need to derive the inside one, and that one has a nested functions, right? And you need to derive one, I think, two or three more. Okay, for online students, do you get the results? Any number you get from the question? Okay, we can work together. Start with the first derivative of the composite functions. So let's write the whole thing. Okay, f prime, and then I'll write ddx of x f x f x. Okay, now we are taking this. Okay, let's move to the next page. Let me copy this. Let me copy here. Okay, now we are going to see that this x and f is both different terms in terms of a function. So we can imagine in our product rule that this is f, g, or if you want to use u, v, also okay. So let's continue. So f prime x. And then ddx, start with x become 1, so just f, x, f, x in that first one. Maybe directly plus, okay, plus the x and f, f prime. It is another chain rule, right? X, x. X, f prime, ddx, x, f, x. Yeah, okay. So close bracket. And then we have this, another chain rule, another product rule. So this make another bracket here. This will be f of x plus x. Finally, I think this will be the last term. So f prime 1. So let's take 1 inside. 1, 1, 1. F1 is what? 2, right? F1 is 2. Yeah, F1 is 2. So this will be F2. F2 is 3. So this will be f prime 3, and this will be 1, f1 is 2, f2 is 3. So this will be 3. This will be 1, 1, 1. F prime 2 is 5. So this will be 5. F1 is 2. 1 F prime 1 is 4. So 6, 8, 48. F prime 3 is 6. F prime 3 is 6. 8, 48 by 8. Okay, let's see. Is there anything wrong here? X1, 3, 5, 8. Wait. X prime. Okay. Anyone find mistake on my equation here? I think 1, 1, 2, 3 plus. Oh, no. I make some trouble here for calculating this. So this will be 6. 6 with 5 will be 30. 30 plus 33 multiplied by 6. Oh, yeah. Yeah. Okay. Yeah. This is already correct. So, yeah. So this will be, let me write down. So this will be 3 plus 5 and 6 like that. Okay. This will be 6, that's a 3, 1, 9, 8. The mistake that I made before is this parenthesis here. So I think this is also worth mentioning. So if you have parentheses, you have addition, multiplication, and or division, and then additional or subtract, or maybe just sub. Okay. Every time you in the mathematics, you start with, if you see any parentheses, start working with this first. If you see any multiplication after the parentheses, start working with this, and then the latest part will be the additional or subtraction. Or if all with the same thing, start from left to right. So this is priority to check. Okay? Sometimes we forget this. Okay. Yeah. Okay. Okay. Let's move on. Okay. Is there any question first for online or in the classroom? Is there any question? I think that's quite correct. Okay. So yeah, start slowly and careful with the sum calculation. Okay. This is just another perspective. Okay. If you have the power rule, like maybe you have 5 minus 3x with power of 6. So if you have y prime here, we can directly write this. Okay. So this is basically what the chain rule, the power rule with chain rule. So it's not really that necessary to keep in mind the formula, but if you already get the principles on how the chain rule works, that should be enough for every derivative, every function that you need to derive. Okay. So not all formula in the textbook has. Hmm? Oh yeah, forget 5 here. Okay, I think we can move to the the implicit differentiation, the next section. And while we can also uh, going back to the chain rule, and I think because most of the time in your calculus problem, we will face a composite function, so that you need to keep in mind that chain rule is always be there. Okay, because sometimes I think when I was in I think junior high or senior high, in my experience, students sometimes they are being told by the teachers, okay, this is how it is, this is how it works, and then when the students is asking why we are doing this and that, the teacher cannot answer, and then how they study is they study chapter by chapter. So every time they are moving to the next chapter, they didn't really remember what the previous chapter. So that is how we are going to have a mistake in calculus, okay, or in math in general, because sometimes in our education system, maybe we work on chapter by chapter by chapter. But in calculus, like for this semester calculus and next semester calculus, they are in line together. And also in other part on your engineering classes, if you're taking more advanced mathematics, like engineering of math, or maybe another, like maybe linear algebra or anything related to math, advanced mathematics, everything is related and everything has a connection. So I hope uh, I don't really want you to memorize all the formula, all the symbols or the terms. At least you know how, and you know, like if you are being given the derivative, you know the very basic foundation of it. And if you forget, like for example, for me, if I were given, like for example, the one that I intend to forget is, like for example, the sine inverse x or tangent inverse x, and asking what's the derivative of this, even though we are not there yet, but I will tell you, like every time you forget about this, we still can go back to where it began, and we can still be able to solve most of the problem. Okay. because in my experience, I also I was quite lazy to memorize all formula. So I always keep in mind like one or two, then that from that one or two I can go for all formula. Okay, so I hope you can do that as well. Okay, okay. Now first, let's look at this graph here. Okay, so this is the another section. It's called the implicit differentiation. So let us look at the circle equations here. It's called the x squared plus y squared is equal 25. Okay. Now, what is the relation between x and y? So what is in terms of the circle equation, what is the relation between x and y? They are just a point, right? They're just a point. Like, for example, if this is x here, so when x is equal 4, y equal 3, and then you get the radius is equal 5, right? You get that in every circle equations, right? You get that in every circle. You will get the radius, right? So x and y is just a point of coordinate. It doesn't mean that x and y has a relation, right? Like, can we say y is function of x in this circle? No. But if you want, we can make it happen in these two functions here, function f and g. We can make it into square root of 25 minus x squared, or the negative one, the semicircle in the below the x-axis. We can make these two f and g happen, right? And we can make y is function of x. Okay. To get uh, more visuals, and it can be uh, transferred in your mind. Let's just work on this. I have some illustration here. I'm in the middle here, and you have, imagine this green line is a ladder. Ladder. So you want to go through that ladder. But then it has slippery wall. So this is the wall. It's slippery, a slippery wall. And then your ladder is falling down. It's falling down. Let me draw the other color. So maybe around here. Yeah, probably there. So it's going down, and eventually it will be falling over to the ground. Okay. It has a ladder has a length of a 5-meter length ladder. This is, let's make it similar to these cases, the circle one. So this will be 4 meter, and this will be 3 meter. Although it's not really proportional, but let's say that's 3, 4, and 5. Okay, maybe to make it more convincing, let's take this and make it into engineering graphs like that, right? Usually, if you are using software in engineering design, this will be a line that looks convincing for engineer, and this will be 5 meter. And you know, this wall or this ladder falling down this direction. So this direction is falling down with velocity 1 meter per second. And then the question arises, how about velocity here? How fast the ladder going to the left direction? So it's asking the velocity to the right. So this is actually rate of change, or you can also relate this to physics, to velocity, uh, and also this is actually, I think in next section in our chapter 3, we will also learn about this, but I will show you this at now because I want to connect this to our implicit differentiation. Okay, so remember, okay, the ladder you have, the green one here, is always 5 meter, right? It's not changes. So when it's going down 1 meter per second, there's also changes in the left direction there, right? So if the green going down and if the green going to the left, okay, and eventually you will need to get how fast that ladder going to the left. Okay, the first thing, if we come up with this question, the first thing we need to have is we name all necessary uh, all necessary terms. Okay? For example, let's say this one is our y-axis or just y, and this is our x. Easy, right? And then because it has 5 fixed constant, we can relate all this with the triangle formula that easy to come in mind. Just relate to this, or maybe use x first to make it more ideal. So we have Pythagorean theorem, right? Okay, and then there is change in time, or to be precise, there is rate of change, right? Rate of change means, if you remember, maybe in physics, if you have some displacement and then you want to know the rate of change, you can write the displacement and then you have over time. And you can also relate this to calculus. So now, if we are going to make this and we differentiate all these terms with respect to time, eventually we will get something that's similar to this ds over dt, or velocity in this case. Okay. Now, if we have this, then we write to x, but it's differentiated to t. So we need to still write dx over dt, and then plus to y dy over dt, and this equals 0. Okay. The one that we are looking for is this dx over dt, and this is dy over dt. In my case here, or my preference, because this 1 meter per second is going to make the y-axis decrease. See, decrease from 3 maybe to some number here. It's decreasing, right? Decreasing, and eventually get 0. And in x-axis, it's got increasing until 5, right? So I prefer to take my dy over dt becomes negative because it's decreasing. Okay, so I want to make it that way. But actually, plus or minus, that's up to you as long as your information is correct at the end. That's fine. But I want to make it negative. So 2x dx dt, or maybe 2x is x is 4, so dx dt plus, or maybe minus 2y is 3, and then dy dt is 1, which I already minus here. And 8 dx dt is equals maybe directly there. So dx dt is 3 over 4 meter per second and going to the left. If you want to make negative and positive by direction, that's also correct. As long as you keep consistent, it's all correct. Okay? As long as you keep consistent, it's all correct. Okay, but I want to make, because it's reduced, I want to make it just negative. So I got this. Okay? And now let's take a look what we did here. So we take something here. Let's say we have some difference in terms of dx, right? And we take something here that is also changes in dy. So we have dx that is reduced and dy that is increasing. Okay. Okay, let's go back to our circle. Let's go back to our circle here. If I take another radius probably here, this is the same radius 5. But if you're looking here, the yellow triangle here, the dy is increasing, but dx is decreasing. But they keep increasing, decreasing, as long as the radius is 5. Right? So if you are going to rotate, maybe going to here, they are going to have another one here. They are going to have another one here. The same radius, different dy and dx. So that's how, okay, eventually we will go to this implicit differentiation. So what is implicit differentiation? So we know that there is no relation. Y and x here. There is no relation because these two are different things. Okay. But if you are looking at this triangle here, although we have include another variable t, if you look closely, if we are just looking this and then, okay, let's derive this. Oh, maybe we can derive this just as dx and then as dy like that. Oh, let's just divide all by dx. It seems that we can get our expression of first derivative. It seems we get the first derivative here. It seems. Oh, can we do this thing in terms of our circle here? Okay, and that is exactly how implicit differentiation works. Okay, so implicit differentiation is we are somehow implicitly derive uh, derive a function as if y is function of x. So that's why it's called implicit, because we are making somehow y is f of x. Okay. So if we have x squared plus y squared equal 25, if we want to derive this, the whole thing here with the dx, derive with the ddx, then x squared just become 2x plus y squared. Let's just treat y as x, so 2y. But let's make another exception in y here and take them dy dx, because we are making as if this y is function of x. Okay, and then it's equal 0. And then we can solve this, and it's getting negative x over 1. And that is how implicit differentiation works. Okay, and this is still okay. So let me write here. So in your calculus, the first semester is about all problem is single variable. We call single variable calculus. The second semester, this is what we call multivariable calculus. Okay. So even though we see that we have x squared plus y squared, we have two variables, we are still working the derivative in terms of single variable x, because we are using ddx, dy dx. We still find that dy dx. Later, in second semester, we learn how to differentiate both x and y, or maybe another term z or w, with terms called partial derivatives. And that is how you exactly derive each variable correctly. But here, you derive as if y is related to x. Okay, and it's actually work. It's actually work. Okay, let's see. So implicit differentiation. Uh, okay. Okay. Although still, if you want to solve this in terms of, let's say, you make it into this one or this one, that's still, I think, okay. I think still okay. For example, if you have xy is 4, 3, like this one, I think you can use the second one here. You can use this semicircle because it's over here. The point is over here. And then you can use this and then derive and find the f prime x. And you can use that functions. But when the functions become more complicated and it's expressed in terms of x and y in one equation, then I think the implicit differentiation will be useful to have to solve those problems. Okay, so what's the thing that you need to at least remember or keep in mind for implicit differentiation? Well, let's just get to some problem here. So find y prime, or maybe find dy over dx. Okay. So if I give you this question, dy over dx or y prime, you know that this means that you need to find the first derivative. So first derivative. Okay, so first we get this, and we derive both sides. So left and right, we derive with respect to x, and this will be 3x squared, okay, plus 3y squared, but adding dy dx for y. And for x, y, this one here, then we came up with the product rule. So 6x or maybe y plus x dy over dx. And multiply 6 here, and then grouping dy dx, 3y squared minus, I think maybe we can just simply cancel this 3 out, and this will be 2. So dy over dx will be 2y minus x squared. Okay. Now the idea behind this implicit, first derive both sides, treat y as x, but adding dy dx. And the third one, solve for dy over dx, because that is the one that you are looking for. If the question is asking second derivative, then so y double prime, then you need to derive one more time from the dy over dx. So dy over dx, you derive one more time, d dx. And you can, I think, directly go to quotient rule. Yeah, it's quite long and really, really complex, I think. Okay, I will stop here. Okay. Now from here, we can actually solve for the problem we have before. So let me give you some time if you want to take some notes from here. Okay, any questions from the online students? Any questions? Okay. Okay. Now let's take another page. Okay, the question that I given is this question here. We go here. How to solve this? Okay, by using the implicit differentiation. First, we can take this y, take squared, and then take squared both sides. Okay, no problem, right? So we have y squared and then x plus this, right? Okay. And by looking at this, you will notice that because in terms of math, this square root of x will go unbounded, right? Infinitely going to be large and larger. X plus x, right? This here is also unbounded. And you see that this is actually our y, right? Right? So we can also think this equation as y squared is equal x plus y. Okay, by doing so and using the implicit differentiation, we can take this and differentiate the terms of x with respect to x. And then this will be 2y dy dx, and then this will be 1 plus dy dx, and solve the dy dx. 2y minus 1 equal 1. So dy dx is equal 1 over 2y minus 1. Usually, the answer for implicit differentiation will, if you have the y inside and you know the equation of y, sometimes we need to exchange that equations back to the original equation. And that's the solution. Okay. So implicit uh, powerful tools in derivatives. Another powerful tools in derivative is the logarithmic derivative or natural logarithmic using the ln. It's also another powerful derivative. And precisely the next section is about the log derivatives. Maybe I will go for a little bit, uh, taking you to the log part. Okay, taking you to the next page. So derivative of logarithmic. Remember, we have the y equal b with power of x. Another, if we take inverse, this will be the inverse log with base b and then x. Or if you remember the e x, the inverse will be y ln x. Right? Okay, let's start from let y equal log base of x, like log base of b of x. And then we can state that from this log, we can write down b with power of y is x. Okay? And because we already learned the implicit, let's try the implicit formula here. This become ln b, right? But we have still write dy over dx because of y here. Okay. And then this equal with 1. So dy over dx will be 1 over b with power of y ln b, or we get back to the original y, that is log or x ln b. And then if b equal e, then we have the dx of the ln x. It seems that it will be 1 over x. And this is another important formula in derivatives. So ln e is 1. Right? So if you have y equal, so example, you have y equal ln and then x cubed plus 1, we can use the chain rule. Remember, this is the outside function. This is the inside function. We can think that FOG, so y is FOG, f is ln x, g is x cubed plus 1. So if we want to derive this, so y prime, so this will be, f prime will be 1 over x, g prime will be 3x squared. So we can combine this together. We can write 1 over x cubed plus 1 multiply with the inside function 3x squared. And sometimes, if you think that the inside functions may be too complex, we can let this becoming another terms. For example, maybe using u or v. We have du dx here, and we can define this in terms of dy dx is equal dy over du over dx, the chain rule. So it's the same principle. Okay, let me give you another example and maybe the last example before we finish our lecture. Find dy dx if y is ln x plus 1 . Okay, let me give you a few minutes to try. Oh, for next week, because I will be in the introduction class. I think next week will be online class. Is that okay? So next week, Friday, for Friday class. Yeah, Friday, only Friday, because it's uh, if you are going to class and then have the online session, I will be rushed preparing this setup. Okay. It will be online. I think next Friday, I think 2 Fridays will be online, and then go back to class. But Monday still we still have class. Okay, any idea to solve the ln? Any idea? Okay. Ah, good idea. Good idea. Okay, your friend suggests to use the logarithm law. Okay, maybe let's try to break down this first. Probably you're thinking that this is will be using the 1 over, let me just write this first, and then the dx of this will be using the quotient rule, and then blah 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 minus blah blah blah, right? But if we're thinking, so this means if you are taking this route, this is directly calculus. So you are using just derive directly using quotient rule. That's the calculus directions. And you get the answers eventually after some process. But you can also think that if you have this, you can also remind that if you have ln AB or log A over B, you can always take this log A minus log B, right? So we can take that as our ln here, x plus 1 minus ln x minus 2, like that. And then it's much more uh, much more human. The before, I think it's sometimes it's complex, and if complex situation happens, sometimes you will make mistake in calculations, right? And we need to avoid that. So this means that this is, you take some algebra, you simplify the root, and after this, then this will be the calculus part. We derive this based on logarithm derivatives. So dy dx will be 1 over x plus 1 minus 1 over, and multiply with 1 over 2. So just 2 lines, and get the result. And in exam, I'm usually giving you questions that just 1 or 2 lines. But getting that lines is difficult. But writing, for me, I don't like to having the students write really long, unless that is the really explore, prove this concept is correct, so that you need to write all possible possible answer, all the logical reasoning, and you need to write that. But if the question is just asking find derivatives or find the equation of tangent line, usually I'm giving functions that are, it seems complicated, but actually you can write it in a short way. Okay. Yeah, I think this is the lecture for today until this part, the log part. Next Monday, I'm still giving you some LN, some part that I think still need to keep in mind. Okay. And then we can move to the inverse of trigonometric. And then I think I will skip some part in chapter 3, especially in the rates of change in physics, chemistry, like that. In the physical phenomena, I think I will skip that. It's much more physics. I think you can learn in physics. So yeah, I will stop this presentation, and let's give you this for feedback time. I hope I already add more time for you to check and see if this time is enough. Okay. Actually, this is the first time in this in this semester I'm using this kind of interactive way to engage with students, especially for online learning. And I think if you want to use this kind of method, maybe with your friends, or maybe with your, if you have maybe activity with, I don't know, maybe club, or maybe uh, organizations that you're actively involved. This kind of tools can help you to get interacted with the other members, right? And also I learned a lot how to use this tools, and helping to build a way that I can interact with students, especially for a teacher. If the teacher wants to see the students, whether they are maybe get it or maybe understand or not, sometimes if they just see the students, and maybe the students just, oh, okay, but the teachers is not really know, oh, how much does he get. Okay, it's okay if you are not learning well, as long as the teacher know, then the teacher will know, oh, the students, maybe the percentage, maybe 50% learn well, maybe 50 not, then the teacher will come up with a solution how to get it right. Okay, let's start. Let's start. Okay, let's start. I have 3 questions for today. I hope It's enough, and the time also enough. Okay, 3, 2, 1. Let's start. So find equation up to the tangent line to the curve at the given point. Okay, 1 minute, 40 something seconds. I hope that's enough. Oh, already answer. 1% of the answer. Oh, very fast. Okay, good, good, good. Okay, 35. Okay, 4, 3. Okay, still half minute, 30 seconds. Four, three, two, one. I hope you get it correct. Okay, this most of you getting correct. In the classroom, you get correct. Okay, okay, let's go next question. Okay, whoa. Who is 32? 32 is your ID, right? Or no? Okay, let's start next question. Okay, I'm just giving you this time, I think short time. Is it true or false? Okay, 30 seconds. Whoa, whoa, why you are answering true? Why? Okay, okay, let's go to the next question. Is 27 here? No? Okay, okay, let's get to the next question. Third question. Okay, 3, 2, 1. Okay, you need to at least calculate. I think one half minute. I think enough. 1/2 minute. And carefully read the number. Carefully read the number. Okay, 45, 4, 3, 2, 1. Okay, 30, 29, 8, 7. Okay, Okay, 20 seconds. Two, one. Okay, I hope you get the correct answer. Oh, good, good, good. In the classroom, you get correct? Correct. Okay. Okay, who is the leaderboard? 27? Is 27 here? No? Okay. Okay, congratulations. Congratulations. All right. Okay, so see you on Monday. And hopefully this week I will return the score to you. So after I checked, some of the students, for example, if the answer is 2, some of you are writing like, oh, y is 2 or x is 2. So sometimes the system doesn't count that as correct. So I checked that, and I think I've checked all of the students, and maybe tonight I will give you the result. Okay. Okay. So thank you, thank you. So finish the lecture. You can leave the Google Meet. Yeah, you're welcome. And don't forget, every time you have the homework for your courses introduction, don't forget to give the deadline. Okay, pay attention to the deadline.